Okay, here is a review from last year. Okay. Everybody good with A, Coulombs.
Should we be taking notes today or just like what?
Okay. That's gotta just a standard international. Yeah, it's something. Yeah, it's like the international standard. All right. So you will need to. I wouldn't necessarily memorize these, but definitely be familiar that a proton is way more massive than an electron, but they have the same charge. Okay. Often you'll see them listed as like a positive E and a negative E for the charge, like one electron. Okay. Um, yeah. And so this is how many. It's like saying, here's one egg. How many dozen is one egg? It's 1/12. How many coulombs is one electron or one proton? It's 1.6 times 10 to the negative 19th coulombs. Okay. So insulator. These are materials that do not allow electrons to transfer readily or easily. They are possessive of their electrons. It's kind of, I would, if I could personify them, I would say it's like American suburbia. Like, I got my lawnmower. Like, you can't borrow mine. Hey, do you want? No, I'm fine. I'm self-sufficient. Like, I don't know you. I say hi to you, but that is about it. And America suburbia. Okay, I got my 8. I'm good. My valence shell is filled. Okay. Versus conductors, they are more, the catchphrase in chemistry is sea of electrons, where it's metallic bonding. So it's not so much, if I could personify that, it's more of like a commune or a hippie community. Like, dude, my electron's your electron. Yeah, that's cool. Like, you can yeah, man. As long as they've got a lawnmower in their neighborhood, we're cool. We're good. Okay. Does that make sense? Okay. So, um, sea of electrons. The idea. Okay. So when you charge by conduction, this is the packaging peanut lab. Yes. Okay. When you touch something that is charged to something neutral, electrons are able to transfer, and conduction charges to the same type of charge. So if you had a negative rod touching your neutral peanut, the peanut becomes neutral as well. Sorry, becomes negative as well. The rod, we're going to say, still is negatively charged. It's just not as negatively charged. Good with that? Okay. Um, so do you know how to do these? Tell your neighbor what you think. Tell them how you got there. Correct answer is C. Okay. What you do is you just find the average of the two that are touching. So +4 plus a -2 gives you +2 divided by 2 to find the average. +1 plus both have +1, and then you find the average of those two. Good with that? Okay. Correct answer is E. Okay. It can polarize. A neutral object can polarize. This is why a balloon that you rub on somebody else's head will stick to the wall. The wall is neutral, but the molecules in the wall polarize. Did you guys do the charge rods to the water, stream of water? Okay, so water is neutral, but it's a polar molecule. So you got the Mickey Mouse ears, hydrogen, more positive, right? And so if there's a negative rod over here, the ears go whoop, attract. If there's a positive strip over there, it's like whoop, and it attracts. Good with that? Okay. If I had, which I don't, but I had a can of Coke and had a negatively charged rod, it would attract. If I had a positively charged strip brought up, it would attract. Okay. Positively charged strip, electrons are going to this side, leaving behind protons, right? Like protons don't move. Good with that? Okay. The electrons are closer than the protons, so the net force is attraction. Bring a negatively charged rod, the electrons run away. The exposed protons are closer to the negatively charged rod than the fleeing electrons. Therefore, there's a stronger force of attraction than repulsion because the protons are closer. Net force attraction. Good? Oh, look at me telling all that stuff. All right. Okay. So, yep, polarization. So it's still neutral. These electrons are closer to the positively charged, so there's a stronger force of attraction than there is repulsion because these are farther away. So the net force is attraction. Okay. Yep. Okay, so this is how this was in a conductor, kind of like the can in an insulator. The electrons are stuck inside their picket fence. Can I go? No, you're grounded for life. Like, oh, okay. So you have a positively charged, let's say a positively charged balloon. The electrons inside the wall are going to the close side of the fence as close as they can, causes the molecule inside the wall to polarize, there's a stronger force of attraction than there is repulsion. Therefore, the balloon sticks to the wall. Okay. Before you answer, I'm going to show you the next question. Does everybody have a vote? Okay, here's the next question. Ugh, stink. Out of batteries. Okay, next question. Did you ever see the difference there? B and C are switched. It's a kick. What in the world? Oh, now it works. Good. Okay, so this is the first one. Tell your neighbor. Okay. This is the second one. Tell your neighbor.
I fully assumed they were.
Okay. Correct answer for this one is C. Okay, this would be an example of charging by induction rather than conduction. Conduct is contact, touching. Induction is kind of like teasing, taunting, like wah, like ah. Okay, so electrons run over. No, electrons are like woo, leaving behind the protons. They separate, negatively charged. Versus the first one is what? Yep. So what's the result? E. Like they respond like yeah, and then it takes away like and they go back neutral, separate, still neutral. Charlie.
Just as a refresher,
Yep.
Only electrons are moving.
Correct.
So you can't charge in like through induction with a negatively charged.
Right? Oh, you absolutely can.
Especially electrons back. Oh yeah.
Yep. You absolutely can. Okay, so here's a traditional induction process. So we bring, this is our neutral object. We have a positively charged object. We ground it, meaning we touch it, we connect it to something that is huge and neutral. Okay. In the lab that you did last year, you were considered huge and neutral compared to the packaging peanut. So when you touched it, it's like adding a bucket of water to the ocean. Like, did you just raise the sea level? Like, no, you didn't. Okay. When you touch the peanut, you're still neutral for all practical. Okay. So in this case, electrons, no. Here you have electrons are over here. The ground is a place where there's an infinite supply of 1-to-1 ratio of protons and electrons. Okay. Electrons are always looking for a better ratio. They are not satisfied with a 1-to-1. If they can find a place where there's 2 protons for every 1 electron, they are totally jumping ship. Okay, they are not loyal. They are going where there's better ratio. Okay, so when you ground this, the electrons over here leaving behind the protons in the ground, the electrons here are like, wow, look at all those exposed protons. So electrons come up from the ground like, hey, how you doing? And then we take away the ground, so the path for transferring is no longer available, and then we take away the positively charged object, and the electrons that were enticed to come over here are like, oh man, they go back home like, what? Ah! And everybody's unhappy. Okay? You could personify electrons. Protons are pretty happy. Okay? Good with that? Good with that? All right. So that was how you charge stuff. So Coulomb's law. So this works like gravity, except it could attract or repel. Okay, you got a constant charge on 1, charge on 2, divided by the distance of separation between their centers squared. Okay, good with that. It is a vector. I would recommend just dropping the positive and negative signs on the charges, finding the number, finding the magnitude, and then use your brain to figure out which direction it's going. Okay. K is 8.99 times 10 to the 9th newtons meter squared over coulombs squared. Okay. Tell your neighbor. Mr. Smiley. I sure can. You're welcome. Bye. Okay, correct answer is B. Has to have the same force, Newton's third law. Good with that? Okay, just like the same gravitational force between the moon and the earth. Okay, same amount of force. They respond differently to the force based on the mass, but okay. So, we are going to, so this is a new term. This is going to be convenient when we start doing calculus stuff. But this constant, the permittivity of free space, E naught, is often what's referred to, is 8.85 times 10 to the negative 12th. You'll see that a lot. And Coulomb's law is written as 1 over 4 pi epsilon naught. You're not wrong to write. So this replaces the K. When we start doing calculus stuff, this arrangement is convenient. Okay. So, permittivity of free space. Okay. I want you to go to the attendance office at some point in your convenience. I don't know. Okay. Thumbs up when you have a guess. Tell your neighbor. Okay. Correct answer is B. Good with that? And this is repelling down. This is repelling to the left. This is repelling in B. You find the resultant of A and B. You still, sorry, A and C. You still get B. Good with that? If they're identical. Correct answer is tell your neighbor. Is everybody good with D? This is repelling. This is attracting. Find the resultant. D. Good? Tell your neighbor.
It was January 6th, 2021.
All right. Correct answer is D to the right. Okay. Here's quick concept that messed with me when I was in your shoes. So if you were trying to calculate the net force, you would do Coulomb's law. With this pair, and you say, okay, let's say I'm going to make this up. Let's say it's 12. Okay. And then you were trying to find between this pair, you do the same thing. I thought that this guy would run interference. Like it'd get in the way, it'd mess things up with this math. Like you can't really. Okay, well that's like saying, okay, I don't know, whatever. This slinky has a certain amount of weight. Okay. If I stick this table in between the earth and the slinky, I just ran interference that this weighs something different now. It doesn't matter. Does that make sense? So with the presence of this or that, like with or without that, this math is going to be identical. It's going to attract, and let's say it's like 10, so the net force would be 2 to the right. Good with that? Okay, so that's electric force. Electric field. This is, the way that I describe this is like it's the promise of an electric force in a certain area. So there's a similar idea of like an gravitational field. Okay, so this tennis ball has a force of gravity acting on it at this location. It's how much it weighs. If I get rid of the tennis ball and I get rid of all air molecules, is there a force of gravity in this location? No, there's not, because there needs to be two masses. Okay, but there is a gravitational field at this location. There's a promise of a gravitational force if something with mass is stuck in that gravitational field. If I take something with mass and I stick it in that gravitational field, this object will experience a gravitational force. It's the promise of a force of gravity at this location. That's what a gravitational field communicates. An electric field communicates the same thing, but it's with regard of, hey, at this location, if you stick something with charge in this field, you will experience a force. It's the promise of a force. And so it's described as, a lot of times, this is kind of where this comes from, but if you stick something with charge in an electric field, you'll experience a certain amount of electric force. This is the promise of the electric force if you stick something with charge in there. Okay? And what we can do is we can take a test charge, kind of like a scout. Often it'll be denoted like a Q sub naught, a Q sub O or 0. And we say, okay, at this location, how much force do you experience? Wow, a lot of force there. How much force do you experience here? Not so much force. And we can map that out and figure out the pattern of the electric field based upon this test charge. You okay with that? Once we have that information, then we can say, well, I don't know how much force is going to be on. Well, I can use that to figure out, okay, if I've got some other some other charge A, I'll know how much force is acting on it if I place it at this location, because I know the strength of the electric field at that location. Does that make sense? So this is kind of like mapping out the area, mapping out the field, if you will. Okay. So electric fields have direction. It's a vector. Again, I would not put in the positive negative signs on your math, but ignore those and then calculate the number and then use your brain to figure out which direction they are. Okay. So positively charged objects create outward directed fields. Negatively charged objects create inward directed fields. It's how it's responding to a positively charged test charge. That's where there's nothing actually moving in that direction. It's just how something's going to respond to a positively charged test charge. Okay. Correct answer is B. Beautiful butterflies going in towards the negatively charged object. Good with that? Okay. What is that? We're going to call that good. I will post a assignment at some point